Hello students, in this video I will discuss isospin, Z component of isospin, hypercharge, conservation of different quantum numbers or conservation laws to find out which type of interaction is given. Means either a given equation is strong interaction, is representing a strong interaction, weak interaction, or electromagnetic interaction. And in last I will discuss the quark structure of mesons and baryons, which we have discussed in the last class. So basically we are going to start with isospin. Isospin quantum number. Isospin quantum number. So isospin quantum number is represented by I. Isospin quantum number is always represented by I. What is the need of this quantum number? What is the need of this quantum number? For this, if we take the example of proton and neutron, here I have taken the example of proton and neutron. Apart from this, I am taking an example of pi plus, pi naught and pi minus. If you consider proton and neutron, they have nearly same mass. Both proton and neutron, they have nearly same mass, but their charges are different, have different charges. Similar case is here. These three pions, they have nearly same mass. They also have nearly same mass, but different charges. If you are considering a strong interaction, then both these particles will not be distinguished by the strong interaction. They will act as a one particle under strong interaction. So what I am saying, if these particles are taking part in strong interaction, they are involved in strong interaction, then they will be considered as one part. Similarly, if we consider these particles, then in strong interaction, they will be considered as one particle, because strong interaction is independent of charge. So these set of particles, behave as one particle in strong interaction, because strong interaction is independent of charge. However, in case of electromagnetic interaction, in case of electromagnetic interaction, these particles behave as different particles. So due to this behavior, one can consider, this type of behavior, one can consider these particles as different states of, one can consider these three particles as the different charge states. So we can consider these particles as different charge states, similar to space quantization in atomic physics. So basically these are three different states. In case of strong interaction, they will behave as the same particle. So we have a single state. So in case of strong interaction, one can consider these particles as single state, but in case of strong interaction, they will split into three different states. Similarly, these protons and neutrons, in case of strong interaction, they are representing a single state, but in presence of a strong interaction, they will split into two states. So to represent this type of behavior, this isospin quantum number was devised. Later on, a multiplet number m is assigned to such particles so that we can indicate the number of different charge states. Later on, a multiplet number m, which is equal to 2i plus 1, is devised to represent the total number of charge states. So this is also an important number. M is equal to 2i plus 1. So now we will discuss different examples, this type of examples we have. So now come to the examples of this type of set, this type of set of particles which behave as different charge states in strong and electromagnetic interaction. In strong interaction and electromagnetic interaction, they are behaving in a different way. In case of strong interaction, they will behave as a single state, but in electromagnetic interaction, they will behave as different state. First, m can be 1. When m is equal to 1, so 2i plus 1 is equal to 1. 2i plus 1 is equal to 1. So this provides us I equal to 0. I equal to 0. It means there is only single charge state. M is equal to 1 means there is single charge state. So for the particles like lambda naught, examples are lambda naught is an example, eta naught is an example, eta naught is another example, and this omega minus, this is another example. So these are the examples of m equal to 1 and corresponding to I equal to 0. So basically if m is equal to 1, it means there are single charge state. Now come to the examples for m equal to 2. This is the case of m equal to 1. Now come to the case of m equal to 2. In this case, if we place m equal to 2i plus 1 is equal to 2, then this will provide us I is equal to half. I is equal to half. So isospin number for these particles is I is equal to 0, and if m is equal to 2, there are total number of state is 2. Total number of charge state is 2. Then for this set of particle, isospin will be equal to 1 by 2. What are the examples? There are different set of examples like proton and neutron. One is proton and neutron. They are different charge state. Their masses are nearly same. They behave in a similar way. They behave as a single particle in case of strong interaction. Like another example is cascade minus and cascade 0. Cascade minus and cascade 0. Another set is K mesons, K plus and this K naught, K plus and K naught. Another set, you can take the antiparticles of this like this N bar and P bar, this cascade neutral antiparticle and this cascade plus bar, these particles. Similar is K naught bar and this is K minus. So basically these are different examples for which m is equal to 2, because here these are two charge state, these are two charge state, these are two charge state. Here we have given 6 examples of two charge state where total number of states are 2. Now come to m equal to 3. Example of m equal to 3. If m equal to 3, then m will be equal to 2i plus 1 and this will be equal to 3. So what will be the value of isospin for this set of particles? It will be 1. So when charge states are 3, isospin will be equal to 1. Isospin is going to be 1. Now examples are here pi plus, pi naught and pi minus. Here there are 3 charge states. Their isospin is 1. Sigma plus, sigma naught, sigma minus. Here we have 3 charge state, multiplicity m is equal to 3 and I is equal to 1. So basically here these are different examples having different isospin numbers. Now basically here for all these 3 particles I is equal to 1. Then how will you differentiate between these particles? Because in case of electromagnetic interaction, In case of electromagnetic interaction, these three particles will start behaving differently. So we also have to distinguish. We also have to distinguish between these particles. Then for this, a third component of isospin, a new quantum number was discussed, or IZ or I3. A new quantum number, another quantum number was devised. So what is the values? What will be the values of this IZ or I3? Values of I3 will be equal to from minus I, its value will be from minus I, it will be minus I minus 1, and it will go to I minus 1, and it will be I. So its value will vary from minus I to plus I. Its value is going to vary from minus I to plus I. So how many states will be here? How many I3 number will be here? They will be exactly equal to its M number. Their number will be exactly equal to M number, because M number is equal to 2I plus 1. So take the example of this. Suppose I is equal to 1. Then corresponding to this I, there will be three values of this. This will be plus 1, this will be 0, and this will be minus 1. Now consider these values for these two examples. So here, corresponding to I3 is equal to plus 1, we will have this state, pi plus state. For 0, we will have pi naught state. And for this will be for minus 1, this will be minus. So value of I3 for pi plus is plus 1. Value of I3 for pi naught is 0. Value of I3 for pi minus is minus 1. Similarly, for sigma plus, value of I3 is plus 1. Value of I3 0 for sigma naught, and for sigma minus, their value is minus 1. So this is the set of values of I3. These are the I3 values for this example. These are the values of. Now if you consider here I is equal to 1 by 2. For I is equal to 1 by 2, what will be the value of I3? It will be plus 1 by 2 and minus 1 by 2. It will be plus 1 by 2 and minus 1 by 2. Now apply this. For proton it will be plus 1 by 2. For neutron it will be minus 1 by 2. For cascade 0 it will be plus 1. For cascade negative, this will be cascade negative, it will be minus half. For cascade negative, it is going to be minus half. Similarly, come here, this will be K plus, this will be K naught. Now, if you consider the antiparticle, for proton it is plus half, so for antiproton it will be minus half. So for antiproton it is going to be minus half. For neutron it is minus half, so for antineutron it will be n bar. It will be n bar. For antineutron it will be plus half. Now similar case is for this one, this. So for this cascade negative, its antiparticle will be cascade positive here. So basically its value will be, I3 value will be minus 1 by 2. And for this, no. This is cascade 0. So for its antiparticle, this will be, for cascade neutral it is plus half. So for its antiparticle it will be minus half. It will be minus half. and for cascade negative it was minus half. So for its antiparticle it will be plus half. Similar case is here. This is K plus, its antiparticle K minus. It will be K minus, this its I3 value will be minus half. For K naught bar it will be plus half value. So these are the values for these cases. And here in this case, because I is equal to 0, I is 0, so I3 will be equal to 0 for all these particles. For all these particles, I3 will be 0. Now, come to the conservation laws. So basically, if you are talking about isospin, then isospin is conserved for strong interaction, but is violated in case of electromagnetic and weak interaction. So this isospin, I can write here, this isospin is conserved for strong interaction, but is violated in case of electromagnetic and weak interaction. So basically this isospin number is conserved in strong interaction while it is violated in case of electromagnetic and weak interaction. While this I3, third component or Z component of this isospin, is conserved in strong and electromagnetic interaction but is violated in case of weak interaction. This I3 here, this I3 is conserved in strong and electromagnetic interaction and electromagnetic interaction while it is violated in case of weak interaction. So this is all about isospin and its third component. Next important quantum number is hypercharge, that is represented by Y. Next is hypercharge. It is represented by Y and its value is B plus S. Hypercharge is represented by B plus S. B is always here. Basically conservation is followed by both B and S. Basically B is conserved in all nuclear reactions, while this S is conserved in case of strong and electromagnetic interaction, while it is violated in case of, it may be violated in weak interaction. So basically this Y will be conserved in case of strong interaction and electromagnetic interaction, while it may be violated in case of weak interaction. So Y is conserved in case of strong and electromagnetic interaction. electromagnetic interaction, while this Y is violated. It may be violated. While it may be violated, it may be violated in case of weak interaction. In case of weak interaction. So this is all about hypercharge. Apart from this, there is one another important formula that is given by Zellman and Nishijima. Zellman and Nishijima formula. Zellman and Nishijima formula. Basically, they find out the relationship between the total charge on a particle, and that will be equal to I3 plus B plus S by 2. They find out this type of relation between third component of the isospin and hypercharge. If you know the value of I3 and hypercharge, then you can always find out the total charge on the particle. So this formula can also be written as Y plus 2 because B plus S is Y. So this formula is known as Zellman and Nishijima formula. If you are aware about these values I3, B and S, you can always find out the total charge. You can also verify for different examples. Now we can summarize at this point. I want to summarize all the conservation laws. So basically at this point I want to summarize all the conservation laws. Suppose we want to differentiate between strong interaction, weak interaction, electromagnetic interaction, then we will utilize these conservation laws. So there are two types of conservation laws. First type of conservation laws, they are known as exact laws. Exact laws. What is the meaning of exact laws? The meaning of exact laws is they are conserved. If a nuclear reaction is taking place and that nuclear reaction is possible, then all these exact laws or exact conservation laws, they will be followed. And if they are not followed, then automatically that will be the indication that will provide us the indication that the given reaction is not possible. There are 8 exact conservation laws. So basically here I am writing the name of laws. Here this is strong interaction, this is electromagnetic EM interaction, and here I am writing strong, this is weak interaction. This is the case of weak interaction. First is energy conservation law. Energy conservation laws is followed by strong, electromagnetic and weak. In all 3 types of interaction, energy conservation law is followed. Second is linear momentum. Conservation of linear momentum. This is also followed in all 3 cases. Next is angular momentum. This is followed in all 3 cases. So first is energy, second is linear momentum, third is angular momentum, fourth is charge, charge. This is also followed in all three interactions. Fifth, 6th and 7th, they are Le. L mu, we have already discussed these lepton numbers. And this 7, L tau. They are all basically they are conserved. These lepton numbers are conserved in all three type of interactions. And last is baryon number, conservation of baryon number. This baryon number is also conserved in all three type of interaction. So these are 8 exact conservation laws which are followed by all nuclear reactions. Now, second type of conservation laws are approximate conservation laws. Second type of conservation laws are approximate conservation laws. Approximate conservation laws. Second is approximate conservation laws. Basically, these laws are followed in 1 or 2 interaction, but they will be violated. They may be violated in the third type of interaction, or they may be violated in 2 type of interaction but followed in 1 type of interaction. So this type of conservation laws, they are known as approximate conservation laws. So here I am writing the name of laws which are approximate conservation laws here. First approximate conservation law is I, conservation of isospin. First approximate conservation law is for isospin. Isospin I have already discussed. It will be conserved in case of strong interaction. But here, in case of electromagnetic and weak interaction, it will be violated. But if you talk about I3, it will be conserved in strong and electromagnetic interaction, but it will be violated in weak interaction. Now, come to third one. This is strangeness number. Conservation of strangeness number. This is S. Strangeness number is conserved in strong and electromagnetic interaction, but it will be violated. It may be violated in case of weak interaction. Next is parity. Parity is conserved in case of strong and electromagnetic interaction, but it will be violated, may be violated in case of weak interaction. Next is charge conjugation. Charge conjugation. Charge conjugation is violated. It is also violated in case of weak interaction. It will be followed in case of strong and EM interaction. And last one is time reversal. Time reversal. It is followed here, but it will be violated in case of weak interaction. So these 6 are approximate conservation laws which are followed in 1 or 2 but violated in other 2 or other 1, last one. So these are basically here I have summarized all the conservation laws in this table. Now we will learn how to write down the quark structures of baryons and mesons. So now quark structure of baryons. We are going to going to learn how to write down the quark structure or how to find out the quark structure of baryons. Suppose I am taking proton. On this proton, what is the total charge on the proton? Total charge Q on this proton is plus E. Total charge on this proton is plus E. This is baryons. Proton is a baryon, so it will be made up of 3 quarks. It will be made up of 3 quarks. There will not be any antiquark here. There will not be any antiquark here. Only 3 quarks will form the baryons. We are aware about this property. So basically this P will be formed by 3 quarks and total charge on this proton is plus E. This is plus E. Now, what is the strangeness number of this P? That is 0. Strangeness number for P is 0. So strange particle is not involved here. Charm number is 0 for proton. So charm particle is not here. Top and bottom quantum number for proton is 0. So basically these 4 particles are not involved here. Only U and D. These 2 particles are involved here. If you have 2 particles, U and D, then how can you write down the structure? How can you create this charge? You can create this charge by 2 by 3e plus 2 by 3e and minus 1 by 3e. So in this way, this will be U, and D. This will be the structure of the proton. Here, strangeness number is 0 for proton. And if you consider the strangeness number of U and D, this is also 0. So from strangeness point of view as well as from charge point of view, this is 0. You can check other things also. You can also check other things. This is baryon. So for this B number is 1. And for this is 1 by 3 plus 1 by 3 plus 1 by 3. So baryon number is also conserved. Here. You can also check isospin. You can also check the isospin. What is the isospin of this P? What is the isospin of the P, or third component of the isospin? Basically, we can find out the third component of the isospin. What is the third component of this isospin? This is T3 or I3. This is plus half for proton. And here for U, this is plus half. This is plus half. And this will be minus half. So this T3 will be conserved. T3 is also conserved. If you talk about I, here I is equal to half, and here I is equal to 1 by 2. This will be 1 by 2. This is 1 by 2. So three isospin of half, half and a half. They are combined. If you find out the resultant of this and the difference between the resultant of this and this, that will be an integer number. So on this side, we will have a spin like it can be 1 by 2, it can be 3 by 2 like this. And when you take the difference between 1 by 2, 3 by 2 and this 1 by 2 on the left hand side, it will always be integer. So what I want to say, basically delta I will be an integer. Delta I will be an integer. So this I number is also conserved. So the structure of this proton will be UUD. This will be the quark structure of this proton. Similarly, you can find out the quark structure of the neutron. For the neutron, come to the neutron. Total charge Q is equal to 0. Total charge on the neutron is 0. Baryon number is 0. Basically for this n baryon number is 1. What is the strangeness number for this? Strangeness number is 0. So strange quark is not involved here. Charm number is 0. So charm particle is not involved here. T is 0 and bottom quantum number. All these 4 quantum number are 0 for this neutron. So automatically corresponding quarks are not involved in the structure or in the formation of this neutron. So we have only 2 options, U and D. We have only 2 options, U and D. So how can you create this? By 3 quarks, this can be plus 2 by 3e. This will be minus 1 by 3e. Minus 1 by 3e. So this will be UDD. So UDD is the structure of the quark structure of the neutron. So the quark structure of the neutron is UDD. You can also check in the same way. Like suppose you want to check I3. I3 for neutron is minus half. And here this is equal to plus half. This is minus half and minus half. So basically this I3 number is conserved here. Baryon number is also conserved. I number is, you can also check. You can check every quantum number here. So the structure of the quark structure of the neutron is UDD. Now come to lambda naught. So first thing, what is the charge on this lambda naught? This is 0. What is the strangeness number of this lambda naught? That is minus 1. So because S is equal to minus 1, so can you tell me which quark carries minus 1 strangeness number? That is S. So one of the quark is S. So here, how can you create this? So one quark is S quark. So on the S quark we have this much amount of charge. So this quark is S. Other 2 quarks will be U or D. They can be U and D. How can you create this 0 charge? This will be plus 2 by 3e minus 1 by 3e. So we will have this option. This will be UDS. So this UDS will be the internal structure. You can check other basically other quantum numbers, conservation of other quantum numbers. Like here, suppose I want to check T3 is 0 for this lambda naught. For U, this is plus half. This D, this is minus half. For this is 0. So this T3 number is conserved here. If you want to check S number, this is minus 1. Here this is 0 plus minus 1. S number is conserved here. You can check every aspect, every quantum number here. And the internal structure, quark structure of this lambda naught will be UDS. I'm not going to check these quantum numbers again and again. This is a homework for you. You can check each and every quantum number here. So this is the quark structure of lambda naught. Come to sigma plus. How sigma plus can be formed? Sigma plus, how much charge it has? This is plus E. Strangeness number is minus 1. Because this is minus 1, so one of the particle is S. So this will be minus 1 by 3e. One of the quark particle is S. One of the quark involved in the structure of sigma plus is S. So how can you create this plus E? it can be created like this, plus 2 by 3e plus 2 by 3e. So this will be UUS. So this will be the internal structure of sigma plus. This will be the internal structure of sigma plus. How can you calculate for sigma naught? Sigma naught. Total charge on this is 0, but strangeness number is still -1. So one of the particle will be strange quark. One of the quark involved will be strange quark. How can you find out this 0? This will be plus 2 by 3e. This will be minus 1 by 3e. So this will be UDS. So this will be UDS. This will be UDS. So here you can observe that both these lambda naught and sigma naught, their structure is UDS, but their color combination will be different. But surely their color combination will be different. So their structure, quark structure is same, but color combination of these quarks will be different. Now come to sigma minus. Now come to sigma minus. Its total charge Q is equal to minus E. Strangeness number, you are aware, strangeness number is -1. So one of the quark involved is strange quark. So this will be strange quark. How can you find out this? This can be find out if we have -1 by 3e, -1 by 3e. So this will be DDS. This will be the internal structure. This will be the internal structure of sigma minus. Now cascade naught. Cascade naught. Total charge on this Q is equal to 0. But strangeness number is -2. Because strangeness is -2, so automatically two strange particles will be involved here. This will be -1 by 3, -1 by 3. So two strange particles are involved here. Because strangeness number for this will be -1, for this it will be -1, so total strangeness number will be -2. Total charge is 0, so it should be plus 2 by 3e. So plus 2 by 3 charge is carried by U. So this will be USS. This will be the internal structure of this cascade knot. Now cascade negative. Cascade negative. Charge Q is equal to -E. Strangeness number is -2. So again two quarks will be involved. Two strange quarks will be involved. So this will be -1 by 3e. So this will be DSS. This will be the internal structure of cascade negative, DSS. Now come to omega minus. For omega minus, charge Q is equal to -E. Total charge, but strangeness number is -3. Because strangeness number is -3, so three strange particles will be involved. -1 by 3e, -1 by 3e, -1 by 3e. So this will be SSS. This will be the internal structure of this omega minus. Now, so basically we have discussed the quark structure. We have find out the quark structure of all the baryons. Now come to the quark structure of mesons. Quark structure of mesons. How can you find out the quark structure of mesons? Basically two quarks will be involved. Two quarks will be involved, or you can say rather than one not quark, it will be one quark plus one anti-quark will be involved. antiquark will be involved here. Here in the structure of mesons, we know mesons are the combination of one quark and one antiquark. One quark and one antiquark. Like we start with pi plus. Total charge on this is plus E. Total charge on this is plus E. Now, what is the strangeness number of this? Is 0. C number is 0. T number is 0. B number is 0. So automatically these quarks and or antiquarks, they are not involved here. So how can you form this plus E with the help of one quark and another antiquark? So automatically this will be like this, plus 2 by 3E, and another should be 1 by 3E. This will be, suppose quark, this is not suppose this is quark, this is U quark, and what is the charge? So this will be basically U, and what will be the charge on D? What is the charge on the D? That is how much charge D has. Sorry, this is plus 1 by 3. D carries the charge equal to minus 1 by 3E. So D, anti-D quark, antiquark of this D will carry the charge plus 1 by 3E. So this will be UD bar. This will be the structure of this pi plus. This will be the structure of the pi plus. What will be the structure of pi naught? Here this will be Q will be 0. This Q will be 0. S will be 0. C will be 0. T will be 0. B will be 0. So here how can you find out this pi naught with the help of U and D? We can find out in two ways. First, it can be plus 2 by 3E and minus 2 by 3E. So this will be U bar. It can be the internal structure of this pi naught. Another method for this is Q equal to 0 can be obtained if we have minus 1 by 3E plus 1 by 3E. So this will be D bar. So basically with the help of U bar and D bar, we can find out this pi naught. So this pi naught is the combined, basically these are two different, basically pi naught, this pi naught is made up of two wave functions, one corresponding to this, another corresponding to this. So this pi naught structure can be written as U bar minus D bar divided by square root of 2. So this is the internal structure of the pi naught. How can you find out the internal structure of pi minus? How can you find out the internal structure of pi minus? Here total charge is minus E. Total charge is minus E. Strangeness number is 0. Other quantum numbers, these three quantum numbers are also 0. I am not repeating this. So this will be minus 1 by 3E and minus 2 by 3E. This will be equal to minus E. So this is D and this will be U bar. So internal structure of this pi minus is DU bar. Now come to K plus. Now come to K plus. Now come to K plus. Total charge on this Q is equal to plus E. What is the strangeness number of K plus? That is plus 1. S is equal to plus 1. What is the strangeness number of strange quark? That is minus 1. So one of the particle involved is S bar, S has charge minus 1 by E, so it will have plus 1 by 3E. Total charge is plus E, so here we will have 2 by 3E. So internal structure will be US bar. So US bar will be the internal structure of K plus. What will be the internal structure of K naught? What will be the internal structure of K naught? Total charge is 0. Strangeness number is plus 1. So it will be plus 1 by 3E. One of the particle involved is the antiquark of S, and automatically this will be minus 1 by 3, only then total charge will be 0. So this will be ds bar. Now come to K minus. Total charge Q is equal to minus E. Strangeness number of this is minus 1. Strangeness number of this is minus 1. So automatically one of the particle involved is strange quark. This will be S. This will be S. It should be minus E. So this will be minus 2 by 3E. So this will be U bar. So this will be U bar S or SU bar, you can write. So basically these are the internal structures of the mesons. So in this simple method you can find out the quark structure of all the mesons as well as all the baryons.